So this chapter's discussion is about inter-VLAN routing. So how do we have communication when we go out there and we create all these different virtual local area networks? So VLANs, again, are used to segment switched layer 2 networks for a variety of reasons that we talked about previously, depending on location, department, responsibilities, anything of that nature, devices, however you want to split up your network. It is a virtual way of creating the same thing that you create in a physical environment with your local area networks. But regardless of the reason, hosts in one VLAN cannot communicate with hosts in another VLAN unless there is a router or a layer 3 switch to provide routing services. So inter-VLAN routing is the process of forwarding network traffic from one VLAN to another. There are 3 inter-VLAN routing options. First one you're going to learn about is legacy inter-VLAN routing. This is a legacy solution. It does not scale well, but we're going to look at it, in the very first lab that you do, which is lab 346. Then we're going to look at router on a stick, which is a much more acceptable solution for a small to medium-sized network, where we take one physical interface and we sub-interface that for our VLANs and then create our subnetworks, and then they act pretty much just like a local area network would. And then lastly, we have a layer 3 switch that we will use using that switched virtual interface, so SVIs. Right now, currently, the only SVI that you have learned about is interface VLAN 1, which the only thing we did was give it an IP address, subnet mask, and a default gateway so that we can have remote connection into the switch if anything were to happen to it. This last option, using that layer 3 switch, is the most scalable solution for medium to large organizations. So, your very first one, legacy inter-VLAN routing, relied on using a router with multiple Ethernet interfaces. Now, each router's interface was connected to a switch port in different VLANs, as you see here. The router interfaces served as the default gateways to the local hosts on the VLAN subnet. So legacy inter-VLAN routing using physical interfaces works, but it has significant limitation. So it's almost like the same thing as you just, using a router to create 2 physical local area networks. I can only have so many area networks that I have Ethernet interfaces on my device. So significant limitation in legacy inter-VLAN routing. It is not reasonably scalable because routers have a limited, again, number of physical interfaces. Requiring one physical interface per VLAN quickly exhausts your physical interface capacity of a router. So this method is no longer implemented in a switch network and is included for explanation purposes only, just to have you be aware of it. So router on a stick, this is our big guy. This is the big one that you learn about. What we do with the router on a stick. It is an inter-VLAN routing method that overcomes the limitation of legacy inter-VLAN routing methods. It only requires one physical Ethernet interface to route traffic between multiple VLANs on a network. So that physical interface is going to be our trunk port on your router, as well as having trunk ports on your switch. So a Cisco IOS router Ethernet interface is configured as an 802.1q trunk, and it is connected to a trunk port on a layer 2 switch. Specifically, the router's interface is configured using sub-interfaces. So again, what we need to do is we go into that physical interface, let's say it's G001, and all we have to do is turn it on. We do not, like we did in normal circumstances, give that particular interface an IP address and a subnet mask. All we do is turn it on. Then, virtually in software, we configure these sub-interfaces. These sub-interfaces are going to identify routable VLANs. So the sub-interfaces are software-based virtual interfaces. Each one is going to be associated with a single physical Ethernet interface, and they are configured in software on a router, independently configured with an IP address and a VLAN assignment. So sub-interfaces are configured for different subnets that will correspond to their VLAN assignment. So this facilitates logical routing. When VLAN tag and traffic enters the router's interface, it is forwarded to the VLAN sub-interface. After a routing decision is made based on the destination IP network, so your router still does what a router does, guys. It still looks at the destination IP address to determine the best path and the exit interface, and then it shoots it out, in this case, the sub-interface that is going to the appropriate VLAN of the destination. If the exit interface is configured as an 802.1q sub-interface, the data frames are tagged with the new VLAN and sent out the physical interface. So they come in the physical interface and then they are sent back out that physical interface. The router on stick method of interface VLAN does not scale beyond 50 VLANs. So here is your concept of inter-VLAN routing on a layer 3 switch. This is the most robust. It is the one that is used today. It is the modern method of performing inter-VLAN routing. We use layer 3 switches and switched virtual interfaces. So an SVI is a virtual interface that is configured on a switch, layer 3 in specific, as shown in this figure here. A layer 3 switch can also be called a multi-layer switch as it operates at layer 2 and layer 3. So that is the difference between a layer 2 switch and a layer 3 switch. A layer 2 switch is just simply a one-to-many connection, and it is simply doing switching. A layer 3 switch has the capability of switching as well as routing. And you'll learn about that the further along you go in your studies. Now, inter-VLAN SVIs are created the same way that you use to create your management VLAN. So think back to when you were doing on your switches the interface VLAN 1. You went into interface VLAN 1, you gave it an IP address, a subnet mask, you turned it on, even though technically you don't have to for the most part because ports on your switch are up. And because of virtual, or because it's done virtually in software, it too should be up. There are reasons that would turn it down, but we don't need to go into that right now. Although virtual, the SVI performs the same functions for the VLAN as a router's interface would. Specifically, it provides layer 3 processing for packets that are sent to or from all switch ports associated with that VLAN. The advantages of using a layer 3 switch, that's much faster because now you can switch and route on the same device. Faster than a router on a stick because everything is hardware switched and routed. There is no need for external links from the switch to the router. It's all one big device. They are not limited to one link because what we're going to learn about, and we'll learn about ether channels a few chapters down, we can use layer 2 ether channels to use trunk links between switches to increase our bandwidth. Latency is much lower because data does not need to leave the switch in order to be routed to a different network. They are more commonly deployed in a campus LAN than routers. The only disadvantage is obviously you're going to incur more expense because a layer 3 switch is much more expensive than a layer 2 switch in a router. So your router on a stick kind of looks like this. G001 is connected to the S1 Fast Ethernet port 05. That is a trunk link. That is going to be used to pass traffic. The S1 Fast 01 port is connected to S2 Fast 01 port, which is also a trunk link. So these are trunk links that are required to forward traffic within and between VLANs. To route between VLANs, the R1 gigabit interface is logically divided into 3 sub-interfaces. One for VLAN 10, one for VLAN 20, and one for VLAN 99. Assume that R1, S1, and S2 have identical basic configurations. Currently, PC1 and PC2 cannot ping each other because they are on separate networks. PC1 is on the 10 network, PC2 is on the 20 network. To enable devices to ping each other, the switches must be configured with VLANs and trunking, and the router also must be configured for inter-VLAN routing. Without a router in this picture, PC1 will never be able to speak to PC2. Now, to configure switch 2 is very similar to switch 1. First thing we do, we go in and we create our VLANs, and then we name them. After that, we go into the interfaces, or we create our interface VLAN 99, our native VLAN. We give it an IP address and a subnet mask. We assign a default gateway. Then we start to put our ports into the associated VLANs. So, port 18 is going to go into VLAN 20 because that's what PCB was plugged into. And port 6, I think on the other end, which was PCA, would go into VLAN 10 if I'm going back and remembering the dynamic correctly. I also have to make sure that FA01 on both switches is put into trunk mode, as well as the connection between my router G001 and the switch port that I am plugged into in the switch. Those all have to be configured as trunks. So the router on a stick method requires you to create a sub-interface for each virtual LAN. A sub-interface is created using the interface ID and then the sub-interface ID number in global configuration mode. So it's going to look something like this. If G001 is my physical interface, so this is my physical interface, my sub-interfaces are going to look like this. Okay, for whatever interfaces that you are going to create. Now understand that these interfaces, just like in a LAN, your physical G001 would be your default gateway. We should all be in agreement on that at this point. These sub-interfaces that you create are also the default gateways for each VLAN. Okay, don't forget, you still need a way to get out of your LAN, regardless of it's a VLAN or a LAN. So again, the sub-interface syntax is the physical interface followed by a period and a sub-interface number. So for teaching purposes, we teach you to use whatever you decide your VLANs are going to be. If you're having VLAN 10, 20, 30, 99 for students, administrator, art, management, also make your sub-interfaces the same numbers so that you keep in unison and it's easier to learn that way. So, customary to match the sub-interface number with the VLAN number. Each sub-interface is then configured with the following 2 commands. Encapsulation.1q. Now, encapsulation.1q is going to require the VLAN number, so keep it the same. This command configures a subinterface to respond to 802.1q encapsulated traffic from the specific VLAN ID. The native keyword option is only appended to set the native VLAN to something other than VLAN 1. Then you have to give it an IP address and a subnet mask. This command configures the IP4 address of the subinterface. This address typically serves as also the default gateway for the identified VLAN. You're going to repeat the process for each VLAN that you have created that needs to be routed. Each router's subinterface must be assigned an IP address on a unique subnet for routing to occur. When all of your subinterfaces have been created, enable your physical interface using the no-shut interface configuration command. I would actually state that you should make this your very first thing you do so that you do not forget to turn on that interface. If the physical interface is disabled, it should make perfect sense to you that subinterfaces are also going to be disabled and you will not have communication. So it kind of looks like this. And what I want you to pay attention to is the numbering scheme. Okay? So, VLAN 10, your description, again, has to be something that is helpful to you. So, I am VLAN 10. I make my subinterface 1.10. I make my encapsulation 10. And I make the IP address 10. For my VLAN 20, I do the same thing. Okay? My VLAN is 20. My subinterface is 1.20. My encapsulation is 20. My IP address is in the 20 network. Keep it consistent. This is a good way to learn. VLAN 99, subinterface 1.99, .1q99, and the 99 network. Okay? Keep it easy for you when you are just starting out. But please do understand, you can name these whatever you'd like. They don't have to be this consistent. This is for us, the human network. Okay? Lastly, you have to make sure you configure that trunk. If you don't configure the trunk on the router, you're not getting out from the switch. Okay, so again, my description should be something like trunk link to S1, and then you simply turn it on. Now, the router on the stick configuration is complete after the switch trunk and the router sub-interfaces have been configured. The configuration can be verified from the hosts, the router, and the switch. From a host, you're going to verify connectivity to a host in another VLAN using your ping command. It is a good idea to first verify the current host IP configuration using ipconfig in your Windows host command. Next, use ping to verify connectivity with PC2 and switch 1 as shown in the figure. Everything should be successful because now it is acting just like a router with physical local area networks. In addition to using the ping command between your devices, the following show commands can be very useful to verify and troubleshoot the router on a stick. Show IP route is going to display the current state of your routing table, so it tells you everything your router knows. So if you look at your routing table and you're missing either the 10, the 20, the 30, or the 99, you have to go back and troubleshoot. Okay? Show IP interface brief, one of my favorites. View a summary of your router's interface. This command will display the IP address, the interface status, and additional information. This is going to tell you whether those sub-interfaces are up or down. Show interfaces is going to provide tons of useful information about the configuration and the status of the IP protocol and its services on all interfaces. And then lastly, show interfaces trunk. This is going to actually tell you which which interfaces you have assigned for trunking. So you need to make sure that the appropriate interfaces have that trunking command. Now, using a router on a stick is simple to implement for small to medium-sized organization. However, a large enterprise is going to require a faster, much more scalable method to provide inter-VLAN routing. This is where we would then flip over that coin and use layer 3 switches to provide inter-VLAN routing. Again, layer 3 switches use hardware-based switching to achieve higher packet processing because everything is done on that one device. Layer 3 switches are also commonly implemented in enterprise distribution layer wiring closets. Capabilities of your layer 3 need to include the ability to do the following. Route from one VLAN to another using simple switch virtual interfaces. Convert a layer 2 switch port to a layer 3 interface, meaning it's going to be that routed port that I spoke about. A routed port is similar to a physical interface on a Cisco iOS router, so it will take an IP address and a subnet mask. A normal switch port will not. To provide inter-VLAN routing, layer 3 switches use those SVIs. So SVIs are configured using the same interface VLAN ID command that we use to create the management SVI on a layer 2 switch. A layer 3 SVI must be created for each one of your VLANs that you need to have routable. So in this figure, the layer 3 switch D1 is connected to 2 hosts on different VLANs. PC1 is in VLAN 10 and PC2 is in VLAN 20. The layer 3 switch will provide inter-VLAN routing services to the 2 hosts. Now understand, there are commands that you would have to do in this layer 3 switch. It's not just going to be as a switch. You have to go into this switch, you have to tell it to act as a router. So then once you tell it to do IP routing, then that switch will take and go with both switching and routing capabilities. So you need to complete the following steps to configure S1 with your VLANs and trunking. First, you create the VLANs 10 and 20 in this example. Then you create the SVI VLAN interfaces. The IP address configured will serve as the default gateway for the hosts. Then you're going to configure your access ports. Your access ports are the ports that you add to that particular VLAN for traffic. So in this example, this port 106 needs to be put into VLAN 10. This port G1018 needs to be put into VLAN 20. Then on the switch, you need to issue the IP routing global configuration command to allow traffic to be exchanged between VLAN 10 and VLAN 20. This command must be configured to enable inter-VLAN routing on a layer 3 switch. Inter-VLAN routing using that layer 3 switch is simpler to configure than a router on a stick. After your configuration is complete, the configuration can be verified by testing connectivity between your hosts. From a host, verify connectivity to a host in another VLAN using your ping. Always a good idea to first verify that your information is correct with the ipconfig Windows host command. Next, verify connectivity from PC2 using your ping. And then your successful ping output confirms that you do indeed have inter-VLAN routing. If VLANs are to be reachable by other layer 3 devices, then they must be advertised using either a static or a dynamic routing protocol. To enable routing on a layer 3 switch, a routed port must be configured. A routed port is created on a layer 3 switch by disabling its switching functions. So specifically, you go into the port that you want to use as a routed port and you put the command no switch port. This command takes it out of its switching capabilities and puts it into a router port capability. The interface can then be configured with an IP4 configuration to connect to a router or another layer 3 switch. So in this figure here, the previously configured D1 layer 3 switch is now connected to R1. R1 and D1 are both in the open shortest path first routing protocol that you see here. You will learn about OSPF in Cisco 3. But this is your routing protocol. So both of these devices need to be told that they're going to be utilizing OSPF. So assume that inter-VLAN has been successfully implemented on D1. The G001 interface of R1 has also been configured and enabled with OSPF. OSPF has to advertise whatever networks they need to advertise. So in this instance, it's advertising both its directly connected networks. It's advertising the 10 network here, and it's advertising the 20 network here. Now, OSPF routing is covered in another course. In this module, OSPF configuration commands will be given to you. You will not be tested on them. You do not have to know how it works. You will learn that in Cisco 3. Now, to complete the following steps, or you need to complete the following steps to configure D1 to route with R1. Use the no switch port command to convert the port to a routed port. Then assign an IP address and a subnet mask, and then do a no shut to enable the port. Next, again, you have to enable routing, so you're going to use the IP routing global configuration command to enable routing on your switch. Then you're going to configure routing using an appropriate routing method. In this example, single area OSPF version 2 would be configured. Then you're going to verify routing. You're going to use the show IP route command. You're going to verify connectivity. You're going to use the ping command to verify reachability. So some common inter-VLAN issues that can arise. There are a number of reasons why inter-VLAN configuration may not work. All are related to connectivity issues. First, you want to check the physical layer to resolve any issues where a cable might be connected to the wrong port. If your connections are correct, then use the list below in this table for other common reasons why connectivity may fail. You could have missing VLANs. So how to fix it, create or recreate the VLAN if it does not exist. So you could use show VLAN brief. That's going to tell you everything about your VLANs, or you could use show interfaces switch port and then ping for testability. I could have a switch port trunk port issue. So you want to ensure that trunks are configured correctly, remembering that you need a trunk between your router and your switch. You also need a trunk between switch 1 to switch 2 in this example. You're going to do your show interface trunk command, and that will tell you what interfaces are actually participating in trunking. You can also do a show running command, which will also tell you which switch ports you assigned for trunking. You could have switch port access port issues. You assign correct, so what you want to do is assign correct VLANs to your access ports. Ensure that the port is an access port and it is enabled. Make sure your host is correctly configured in the wrong, or is not correctly, wait a minute. Make sure that your host is not incorrectly configured in the wrong subnetwork. So use your show interfaces switch port command, your show running interface command, and also IP config. You could have router configuration issues. So look at your router sub interfaces, their addresses, make sure that they are not incorrectly configured. Look at your router sub interfaces to make sure that they are also assigned to the same appropriate ID, which is why we always say when you are learning this, keep everything consistent. VLAN 20, network 20, IP address 20. You could also have some examples of inter-VLAN routing problems. As such, the topology will be used for all of these issues. So here's my topology. Again, here are my two trunk links. So G00 with a subinterface of 10 is in VLAN 10 and it has an IP address of 10. Likewise for 20 and 30. So an inter-VLAN connectivity issue could be caused by a missing VLAN. So the VLAN could be missing if it was not created, it was accidentally deleted, or it is not allowed on the trunk link. When a VLAN is deleted, remember, any ports assigned to that VLAN become inactive. So you need to move the ports out of the VLAN before you delete it. So right here you see that VLAN 10 is indeed inactive. Recreating the missing VLAN would automatically reassign the host to that VLAN. You're going to use this, show interface ID switch port command in order to verify the VLAN membership of that port. You can have trunk port issues. Another issue again includes misconfigured switch ports. In a legacy inter-VLAN solution, this could be caused when the connecting router port is not assigned to the correct VLAN. With router on a stick, however, the most common cause is a misconfigured trunk port. So you want to verify that the port connecting to the router is correctly configured as a trunk link using the show interface trunk. If that port is missing from the output, you want to examine the configuration of the port itself with the show running config and the appropriate interface. So right now I can see that I am trunking on native VLAN 1 and I am trunking for the VLANs 1, 10, 20, and 99. So my ports listed here, my allow VLANs here, my native VLAN up here, and my status is trunking, and it is on. When a problem is suspected with a switch access port configuration, use verification commands to examine the configuration and identify the problem. So a common indicator of the issue is the PC is having the correct IP address but being unable to ping its default gateway. So use your show VLAN brief, show VLAN interface, switch port, or show running to verify the interface VLAN assignment is correct. Router on a stick configuration problems are usually related to sub-interface misconfigurations. So verify your sub-interface status using the show IP interface brief command. Verify which VLANs each of the sub-interfaces is on. To do so, use your show interfaces command, which is useful, but it generates a lot of information. So get used to using your pipe command that you see here. When you utilize your pipe command, you are telling to go specifically to a place. So I want to see interfaces is my pipe command, include my gigabit. Here's my pipe command, but only those that are configured with 802.1q. So when I look at this, I see that right here, my interface is VLAN 1.10. My 802.1q encapsulation VLAN is for the VLAN of 100. This is incorrect. I would have to go back and change this to VLAN 10 in order for this to come up. And that's pretty simple. So again, any questions, reach out to me via email. And we are going to apply this firstly to lab 3, 4, 6 and work our way from there.